Okay, aloha, students. Welcome to this last section of chapter 12. And so we're going to summarize the different methods that we learned to count. Okay, so in this chapter, in the nature of counting, first of all, if you had noticed, all the countings are whole numbers, right? So whole numbers when we count. Sometimes I don't think we ever count zero. Actually, to be more specific, I think it should be all our answer when we are counting is natural numbers, right? So, rarely do we count zero. So zero plus natural number is whole number, right? Remember that? And so there's no fractions. When we start getting into the probability, then we will start getting some fractions, right? And so make sure you know the difference between counting and probability that we are heading next. So all this section here, we are counting by natural numbers like 1, 2, 3, 4, 5, right? And so because we are summarizing, make sure that you know the method that we are using here does not really apply to the simple event, meaning just one event. And usually simple event, you don't need the complicated ways of counting, just whatever number of elements in the set will be the number of choices you have, right? So all these fancy methods that we are using here only apply to compound events, okay? And with that said, make sure you don't overkill, only use this fancy way of counting to save time when we are in a compound event, okay? So the first method that we have learned that we call it the FCP, stands for Fundamental Counting Principle. And this is one method that is the least, I can't spell least restrictive. Okay, so that means it applies to a wide range of cases. Okay, and so if your task A is performed n ways and your task B is performed n ways, then a task A followed by a task B is completed by m times n ways, right? So that's what fundamental counting principle says. So you still have some type of ordering. The A is still before the task B, right? And so in itself, the fundamental counting principle have some ordering. So then the fundamental counting principle, the choices in the first task can be reused, right, in the subsequent task. So whether it can be reused or cannot be reused, both fundamental counting principle will work. Okay, so each task can be from the same data set or different data set, same or different, so it both works. So it's a wider range of cases. So it's the same data set or different data set, both works for the fundamental counting principle, right? And it can be reused or cannot be reused, both work again in the fundamental counting principle. But in nature, counting principle, the fundamental counting principle actually closer related to the permutation than the combination. Okay, so we're going to see that in our examples as we summarize. So the next thing we want to set apart from the fundamental counting principle, the permutation is still somehow related to the fundamental counting principle. However, it only a subset of the fundamental counting principle, only in the case of the first task cannot reuse, the choices chosen in the first task cannot be reused again in the subsequent task. Okay, and of course that applied to the combination as well, and all tasks had to be chosen from the same data set, one data set. Otherwise, again, this doesn't work. Okay, so permutation and combination have to have this both requirement. Choices cannot be reused, and it had to be from the same data set. Okay, so permutation combination has the same prerequisite. However, one thing set them apart What is that one thing? If you still remember, that one thing that set permutation and combination apart is permutation when order matters. And order matters means, how do we know if order matters? If there's title, positioning, or labeling involved, then order matters. Okay, so order doesn't matter when we don't have any title, don't have any labeling, and not in a line, no positioning, then order does not matter. And one of the immediate one that we do a lot is, the hands, the 5-card hands in the standard deck of 52 cards, right? So the order doesn't matter. That is a good example of that. Okay. But they both still, choices cannot be reused, and that's where factorial comes in. Is every choice that, every task that you do, you lose a choice in the next task, right? For both permutation and combination. Okay. This new one, new name that we're going to put on this permutation, it's called the distinguishable permutation. It's generally permutation, but some part of the permutation part order does not matter. So it's basically a hybrid of the permutation plus the combination, partially permutation plus partially combination. And we actually did this, we just didn't give the name, the proper name, distinguishable permutation in 12.1. Remember, we had to rearrange the letters in the word book, right? So this O, the two O's, order doesn't matter. We say we treat it as permutation first. That's same as P4 choose 4. And then we use division to take away the two O's, that order does not matter, right? We did that, I believe, was one of the later questions, one of the last questions in 12.1, right? And in 12.2, we did something like this too, right? We had the 12 children family. We say to have 4 boys and 8 girls. How many ways can you have that, right? And so if you use BBB for the 4 boys, BBBB, and then for girls, for the G's, you have 8G. And so because assuming you don't have triplets or quadruplets, each birth is a task. And so basically each time you have either 1 boy or 1 girl, you don't have triples and a twin, then this is kind of like same as rearranging the letters in a word, except this is not really a word, right? A word doesn't make sense, but it's still same idea of rearranging the B and G's. And so total, we treat it as all order matters, 12 factorial, and then take away the 4 boys that order does not matter, and the 4 G's, the 8 G's that order does not matter, right? So this is treat them as order all matters first for all 12, right? So it's like 12 permute 12. So always start with treating them as order all matters, and then use division to take away the ones that order does not matter. Okay, I hope you still remember that from 12.2. And so that we're just giving it an official name called distinguishable permutation when partially order matters. So treat them as permutation first, and then take away the one that order doesn't matter by division. Okay, so the very, very obvious example will be all the letterings in rearranging the letters in a word when there is a repeat word, repeat letters. Okay, so math itself don't have any repeat letters, and so it's actually all permutation, right? This is not distinguishable permutation because none of them order doesn't matter. So this is 4P4, 4 permute 4 is the same as 4 factorial, and that is 24 ways, right? So math, to rearrange math, is not distinguishable permutation because there's no letters that order doesn't matter, right? The second example, however, we have 3 A's repeating. So then this is a distinguishable permutation because we treat them as order all matters first by doing the 6 factorial, And again, 6 factorial is the same as 6p6, 6 per mu 6, order all matters. And then we use division to take away the ordering of the 3 A's, right? So this is partially order matters. Unlike math, there's no repeat A's, right? So this one has 3 repeat A's. We divide by 3 factorial, okay? And this next example revolves, rearranging the letter in the word revolve. We count it as order all matters. 1, 2, 3, 4, 5, 6, 7. 7 letters in the word revolve. And then 7 factorial means 7 per mu 7 means order all matters. And then use the division here to take away the part that order does not matter. So the 2e, order doesn't matter, we will divide by 2 factorial. And then the 2v's, the order doesn't matter because it's the same. Then we divide another 2 factorial. Make sure that both the 2 factorials are in the denominator for takeaways. Okay. All right. So again, this last one, we did it before. We just didn't call it distinguishable permutation at that time. Okay. So this box here, to summarize again, fundamental counting principle is for compound, right? Compound events. Don't overdo it if it's not compound event, if it's a simple event. And it's the least restrictive one. It can be from different set or from same set, right? The test, compound events means more than one, right? So the different tests could be from the same set or from different set, and the choices can be reused or not reused, right? So it's less restrictive, right? But these other 3 that follows the fundamental counting principle are have the same prerequisite. They all have to be from the same set of each task. And the choices all cannot be repeated, okay? So they are prerequisite, they have 2 prerequisites. This data have to be, the choices, the tasks have to be from the same data set. And the choices that used in the first task cannot be used in any other subsequent task, right? So again, what sets the 3 apart, permutation is order matters, right? Order is important. And then the combination is order is not important, right? And the last one is a hybrid of the 2, so partially order matters, okay? And so repetition are all not allowed in this later 3 methods, okay? And so in our practice, it's important to start with which method we are use, and sometimes it is possible to use multiple method, okay? And sometimes fundamental counting principle can be used when there is actually permutation too, okay? So fundamental counting principle does share with permutation sometimes what I call the gray area that both method works. Okay, so let's try number 1. Okay, so read the question. If I have 3 pairs of pens, the units for the pens is pair. Okay, doesn't mean you have 3 times 2. Okay, so it's still 3 pairs, and then 4 shirts. So these are 2 different sets, and we need to separate the set because you don't want to choose 2 pens or 2 shirts, right? So the pens and the shirts should be separated into 2 different sets, right? And it's 2 tasks, and actually we're only choosing 1 task from each set, right? So because it's 2 different sets, this is fundamental counting principle only, because the other ones you have to use from the same sets, right? So there's no gray area. You have what? Each one of these tests is a simple event by itself, right? So you have 2 of them, you multiply them together. So you have 3 choices for your number of pens to choose from, and then 4 shirts for the number of shirts to choose from, 1 pen, 1 shirt for your outfit. So we have a total of 12 outfits for number 1. Okay? I hope that makes sense. Okay? And what about number 2? What do you think? Okay? So here for number 2, I am choosing the pants, 5 pairs of pants, shirts, and shoes. Okay, so how many outfits? So I have 3 tasks where I have to wear pants, and I have to wear shirts, and then I have to wear shoes. And again, this is 3 different sets, right? So it's not from the same set. So if it's from a different set, automatically fundamental counting principle is the only choice, right? Because it's the pants and the shirts and the shoes are different sets. I'm not going back to choose another pair of pants or another pair of shirt or another shirt. Shirt is not pairs. Okay, so then I just times it together by fundamental counting principle, and there's no other way we can do this. And so then you have 150 outfits possible. Okay, hopefully I did my math correctly. I did my mental math. Okay, so what do you think? What do you think of number 3? Okay, so maybe before you copy my answer, maybe you can pause the video and think what you think before writing down the answer I'm about to write. Okay, so this is long time ago. We have 4-digit iPhone passcode. Right now, I think we have too many iPhones. My current iPhone, the passcode is it's not 4-digit anymore. It's 6-digit. Okay, so anyway, 4-digit, right? So digits are each digit is 1 task, right? Because you're punching into the iPhone each time is 1 action. So this is from the same set. Digits are 0 to 9, and believe it or not, 0 to 9 is 10 numbers, 10 choices, right? But can I reuse, right? This is the same set, but second question is, can I reuse the one that I choose in my first digits in the passcode? Okay, so for most of the passwords, you can use like A if you want, right? So you can reuse the digit you choose in the previous task. And so you actually don't lose a choice. So each task, you still have the 10 digits to choose from. And because I can repeat, this is no gray area. I cannot use combination or permutation. It's fundamental counting principle. And so you have the 10,000 possible passcode. Okay? All right. So do you want to stop the video and give number 4 a try and see what happens if we're going to agree or not? Okay? Pause the video. So hopefully you write down something for number 4. So number 4, remember fundamental counting principle. Even though the digits cannot be repeated, we can still use the fundamental counting principle, because fundamental counting principle actually covers more area than the other methods, right? So if you go the first digit, you have 10 choices, 0 to 9, and you lose a choice in the second task when you are pressing the second digit, because you cannot reuse the one that you pressed already in the first digit. And so you keep losing 1 choice. So it's 10 times 9 times 8 times 7. You will get 5,040. And also you can see it as permutation because it's from the same set of data, the first criterion of permutation. And also the choices cannot be reused or repeated. So that fits the permutation. When it's a passcode order matters, we have 10 permu4 will also give you the 5,040. Okay, so either way, this is what I call the gray area. Only the fundamental counting principle and permutation has this gray area that you can use both. Okay, and that is only if they are from the same set. Each task is from the same set, and the choices cannot be reused. Okay, so then you can use both if fundamental counting principle and permutation both order matters. And so only these two will have the gray area. Fundamental counting principle would not share with combinations, actually. Okay, so only the fundamental counting principle share with permutation sometimes. Okay, so number 5, we talk about the deck of cards, right? Deck of cards is always obviously is combination, because when we switch the order in our 5-card hand, it's still the same hand. And so it's combination. And there's combination doesn't share any gray area with, the fundamental counting principle. And so this one will be C. How many choices we have in the first test? 52. And I'm choosing 5 tasks, 1 card at a time, right? So 5 tasks with order doesn't matter. And so we did this in the prior chapter, and the answer is 2,598,960 ways. Okay, and please don't trust me with my computer calculator, because sometimes I do copy it right and sometimes I do copy it wrong. So make sure you double check and get the same answer as me, or you challenge me. Okay. All right. So why don't we try number 6 to 8 on our own? Okay, and come back again after you try. Okay, you have to feel comfortable writing down your own answer, and even if it's wrong, to feel comfortable, make some mistakes and learn from it. Okay, so I want you to, again, if this is in a class, pause the video, work on your own, or work on it with your friends, and come back and let's compare answer after. Okay, thank you. Okay, and I hope that you have some writings in your number 6 to 8, so we have something to compare. Okay, so on number 6, it's always important to kind of identify how many tasks you have, right? So it says how many standard license plates are possible in the state of Hawaii. The standard one, if not the special order one, it always have 3 letters in the front and 3 numbers, which we also call digits, in the back. Right, so sometimes I think I do see the letters repeat or the number repeat, like 002 or like SSP, that type of letterings in the license plate, right? The letters do repeat. And so the standard one is actually how many letters in the alphabet, right? So it's 26, is it? It didn't say vowels or consonants, so 26 letters in our alphabet. And because you can repeat, right, in the S and S again. So if you can repeat, then and you don't lose a choice, so it's 26 and 26. And then the digits is 0 to 9, and if you can repeat, then it's 10 and then 10 and then 10, and then so you multiply them all together, and that will be giving us the total of 17,576 and 76,000 possibilities. And because the choices can be repeated, this is not possible to see it as a permutation, right? So this is not permutation because the choices cannot be repeated, is required for the permutation. So this one's definitely not permutation. Okay. So number 7 is the same problem, and if they say that no repetition or choices cannot be reused again, that's what no repetition means, then possibly we can see it as a permutation. So we can see it as a fundamental counting principle too, right, with the permutation. So we can do the letters start with 26, but because choice cannot be repeated, whatever we chose in the first letter, we cannot use it again. So we got 25 left to choose from, and then the next one lose another choice, or 24. But the next one is number, right? So I don't go to 23 because that's letters, right? And so the digits 0 to 9 only had 10, the first choice. So this is different set, right? Different set. And then the next one is going to be what? Because I lose a choice, so it's going to be 9. And then I lose a choice again because I cannot use it again, the same choice, right? So I lose a choice with each task. And so the answer is 11 million. 232,000 possibilities. Okay, and how can we see this as a permutation? Can we see this as a permutation? This is two different sets, but within the same set, I can see it as a permutation. So for choosing the letters, I have 26 letters, and I'm choosing the first 3 to be letters from the 26 letters. So I can actually see it as permutation 26 permute 3, because no repetition is allowed qualify for the permutation if I limit this first 3 from one set, and then the next 3 is from the 10 digits, and I'm choosing the 3, right? So if you multiply this 2 permutation together, you should get the same answer. Okay, so you can try it and see if that works. Okay, if not, we can talk. Okay, so I am pretty sure it's the same. So there's 2 ways to look at it. That is what I call the gray area. Okay, and number 8, again, we can see it as fundamental counting principle, because order does matters when they involve the labelings or the titles here, right? You have 3 positions that has titles, and so you have 20 people to choose from to be president, but after you choose the president, you have only 19 people left to choose to be the VP, because you can choose the same person again, and 18, right? So this is if you want to see it as fundamental counting principle, and you will get the answer of 6,840 different ways, right? And again, if the choices cannot be repeated, you can also see it as a permutation. And so you have 20 people to choose from, and you are choosing how many tasks? 3 of them, right? So if you do 20 permute 3, you will also get this same answer. So this one is again what I call the gray area. You can see it as a fundamental counting principle, or you can see it as a permutation. Okay, so either way will get you the same answer. That's the wonderful thing about mathematics, is as long as it makes sense, you have more than one way to do it. Okay, you have more than one way to do it if it's mathematically sound. Okay, so number 9. Okay, number 9. I want to do number 9 and number 11 together to tell the difference, because it's all flipping a coin. Then I will do number 10. Okay, so when you are flipping the coin twice, it means you have 2 tasks, right? 2 actions, so you have 2 tasks. And so you can actually see it as fundamental counting principle, 2 tasks. And because your possible outcome for your coin is head or tail, right? So you have 2 choices for your first flip, right? And can you flip the same outcome as the first flip in your second flip? Can you, if you had a head in the first flip, can you get a head again? Yes. So this one is only fundamental counting principle, because you don't lose a choice, right? So this is, you cannot see it as permutation. So your total number of outcome is by fundamental counting principle, so it's 4 ways. Okay, and remember the word total here is very important. If you're counting the total, and the only way to count the total number of ways for flipping a coin or anything that has 2 outcomes, it's actually fundamental counting principle. Okay, so if I think about it the same way for number 11, fundamental counting principle, if when I'm flipping 3 times, I have 3 tasks, right? So each one I'll have head or tail. Head or tail, I don't lose a choice, because I can repeat head or tail, right? So I have total of what? 8 total. Very important. This is total number of ways. Okay. However, if they are not asking for total number of ways, they are asking for specific out of this total, that specifically you wanted to have how many are one tail, right? So tail, head is one tail, right? Because you flip it 3 times, right? Or head, tail, head, right? Or head, tail. Those are the 3 flips with 1 tails. So this is asking you for out of the 8 total, how many are 1 tail, right? How many are 1 tail? And so this actually turn this problem, if you want specifically how many tail or how many heads, it's not total, then we turn this into a distinguishable permutation method, because it's basically how many ways can you rearrange the letter THH, right? So it's treated as permutation, all 3 letters first, and then take away the 2 H's. That order does not matter, so this is called the permutation, distinguishable permutation method, right? So partially order matters, so that's 3, right? So when you do it this way, you actually get the 3, and when you write it out, it is the 3, right? So 3 ways. So again, the difference between number 9 and number 11 is number 9 is asking you for total. So when it's asking for total, you will use the fundamental counting principle to get the total. But when they ask you for specific number of tail or specific number of head, that you are actually asked for different ways that the 1 tail can be in different order, and so it's actually a distinguishable permutation. Okay, hopefully when we give more examples, you can tell the difference between number 9 and number 11. Again, when it's the total, you use fundamental counting principle. When it's specifically how many tails, it's the distinguishable permutation. Okay? And number 10 is very obvious. Every time you have a letter rearranging with some repeats, like assuming the capital A and the small letter a, the lowercase a, is considered the same, then this is obviously distinguishable permutation, right? So treat it as permutation first for 7 factorial, right? And then take away how many, order doesn't matter, is 2 factorial. Right, so that's how the distinguishable permutation works. It's treated as 7 permute 7, which is 7 factorial, right? And then take away the partial part, that order does not matter, and so that will give you the distinguishable permutation way of rearranging the letters in the word America, which is 2,520 ways. Okay, so that's the answer. Okay, let me box the answer so we are not confused here. And this one here is a total, but they are not asking for total, they are asking for specific, so it's the 3 ways. So make sure you are not confused about which way to do. The specific ways with 1 tail is the distinguishable permutation. Okay, so hopefully with more practice we don't get confused with the one in number 9 and number 11 confused. Okay, so why don't we do number 12 and 13 on our own? Okay, and we'll come back with 14. 14 is hard, so pause the video, do some of your own work for number 12 and 13, and hopefully we are comfortable making some progress here. Even if can be wrong, it is fine to learn from mistakes. Okay, so I'll come back and check on answer with you. Thank you. Okay, hopefully you have something on your paper that we can compare. And so number 12, whenever we are rearranging letters in a word with repeat letters, then it's always distinguishable permutation. So we have the total 10 letters and treating it as order all matters. The 10 factorial is the same as 10 permute 10. That's counting all the 10 letters, order matters. Then we use division to take away the 2 E's, that order doesn't matter here, and the 2 T, order doesn't matter, So 2 factorial for the 2e, and then 2 factorial for the 2t, and another 2 factorial for the 2i's in the word repetition. Okay, so when you enter that all into decimals, 453,600 ways should be the answer. Hopefully I didn't copy the numbers from decimal wrong. Okay. Okay, so number 13, remember when do we use the fundamental counting principle and when do we use the distinguishable permutation? Okay, so the fundamental counting principle is when you are asked for the total number of ways, right? So of all different kinds, total number of ways, and that in this case will be 2 times 2 times 2, because each one you have head or tail, so you're going to have total number of ways will be what? 2 to the 5th or 32. But think again, is this what they are asking? Okay, did they ask for total in any part of the question that says total number of ways to flip the coin 5 times? They didn't ask for total, and in fact, they asked for specifically 2 tail, right? So 2 tail, we just write down 2 tail in a 5 flip, so you cannot just leave it at 2 tail, right? Because there's 5 flip, so that means the other 3 is head, right? So in other words, it's asking you how many ways you can rearrange in these letters that is not words, or not a word that makes sense to us, but it's still letters, right? So it's still the distinguishable permutation every time we are rearranging letters. Because you have 5 flips and it's given 2 tail, that means the other 3 are heads, right? So again, 5 letters, so we're going to count it as order all matters, 5 factorial, and take away the order doesn't matter. The 2 tail is 2 factorial, that order doesn't matter. And then the 3 heads also have 3 factorial that we need to take away the ordering, right? So then the 10 ways is the specifically for the 2 tail, right? For the 2 tail, because they are not asking for total. Okay, so total is 32. It's like 1 tail, 2 tail, 0 tail. All the possibility combined is 32. Okay, so make sure that you were able to find the keyword to help you decide which method to use. Okay. All right, so 14 is probably the hardest concept of this chapter, actually. So I'm going to put triple star here. Every time we see the word at least, what does it mean by at least 1 tail? Okay, so because we flip the coin 3 times, so the most we can get is 3 tail, right? So we could get 1 tail, we could get 2 tail, and we can get 3 tail, right? Because I only flip 3 times, I can't get 4 tails, can I? Not possible, right? Because I only flip it 3 times, so the maximum number of tails I can get is 3 tail. But can I get 0 tail also? Can I get 0 tail possible? How does 0 tail look like? Right? So 0 tail is what? All heads. That's what 0 tail means. 1 tail means what? 1 tail, 2 heads. And 2 tail means 2 tail, 1 head. And 3 tail means what? Tail, 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 right? And so if you want to see how many of the 0 tails you have, there's only one way to rearrange if the letters are all the same, right? So all heads or all tail is going to be one choice, right? And then if it's 1 tail, you can treat it as a distinguishable permutation. So that will be 3 factorial, and that's if order all matters. So divide by the 2 heads, that's the same. Take away the order doesn't matter, and so that will give you the 3, right? So 3 here, 3 here, 3 1 tail, and same thing. 3 factorial, and this 2 factorial here that we are taking away is for the 2 tail, and so it's another 3, right? So if you have 1 plus 3 plus 3, plus 1, you get 8, right? And that is what? Remember, if we did it in the previous problem, if you flip the coin 3 times, you're supposed to do the FCP if you want the total, right? So it's 2 times 2 times 2, right? So the total is 8. Okay, so the total is 8. Right? So by the fundamental counting principle, when we are looking for total, right? And so which one is at least 1 tail, right? Which one of the 8s are at least 1 tail, right? Okay, so this is an English test here, not really a math, right? At least 1 tail means 1 tail, 2 tail, 3 tail are both at least 1 tail. So it's this. So it's the 3 plus the 3 plus the 1. So the answer should be 7 ways, right? Because that's the at least 1 tail. Okay, so sometimes it's faster to find the total, which is 8. We use the fundamental counting principle and subtract what we call the complement, right? The complement is the one that is not at least 1 tail, right? And not at least 1 tail is head, and head is easy to count. It's always 1, right? It's always 1, and so you will subtract 1. So sometimes you want to do it all out if you have time, but easier sometimes to do the complement, right? So complement is find the total by the fundamental counting principle, and then take away the one that is not at least 1 tail, right? Not at least 1 tail means 0 tail. Does that make sense? So this is not at least 1 tail, so that's what we call complement. So you can count the one that's at least 1 tail, that's a lot of cases, or count the total and take away the one that is not at least 1 tail. You will get same answer either way. Which way is easier? Okay, which way is easier? Sometimes we do have more than one way to do things, and depending on which way you think is easier, you can decide which way you want to do. Okay, so this 14 maybe not too much difference between the number, the different ways of doing, but number 15, if you flip the coin 7 times, maybe it does make a difference which way you choose when it's at least 1 head. Okay, at least 1 head. So what does at least 1 head means, right? So we can find the total if you want, right? So the total is always the fundamental counting principle. 7 times means you have 7 tasks. So it's 2 times 2 times 2 times 2 times 2 times 2 times 2. And because you have 2 7 times, it's 2 to the 7, and that's 128 total number of ways. And again, this is total. Okay, this is total. And to get the specifics, we can get what? 0 head. 0 head means what? All 7 of them are tail, right? Or we can get 1 head, right? And that means head, and the rest is tail. And then we can get 2 heads, and we can get 3 heads, and we can get 4 heads. How many heads can I get up to, right? And 5 heads, right? Running out of space. 6 heads, and 7 heads, right? And how does 3 heads, 2 heads look like? 2 heads will be head, and the rest tail. And the 3 head will be head, and then the rest tail. And 4 head will be head, and 3 tails, right? And so except the one that's all the letter is the same, the 7 heads and all the 7 tail, the other one we need to use distinguishable permutation to help us find the numbers, right? So 1 head, 6 tail will be what? Counted as all order matters, and then divide by 1 head. There's no issue about ordering, but the 6 tail we need to take away the order because they are all the same, so that's 7. and then the 2 heads will be, again, start with 7 factorial and then divide by the 2 heads. Order doesn't matter. And then the 5 tail, order doesn't matter. Okay, I'm not sure what that answer is. I'm just going to take out the calculator and see. That's going to take me a while if I do it this way, right? So, okay, let me see. So that one is 21, right? So you can keep going and going, and then the next one will be 7 factorial, 3 factorial, 4 factorial, right? And it's going to take me a while. Which one of all this possibility is at least one head? Which one is at least one head, right? So is 1 at least one head? Is 2 at least one head? So all this is what? At least one head, right? So this is understanding what English at least one head means, right? So all these cases, you have to add it all together, 7 plus 21 plus whatever, keep adding until you add all the cases up. So which one is not at least one head, right? Not at least one head. That is actually the 0 head, right? 0 head is not at least one head, all right? So the not is the complement, right? So that's the complement. So we can actually, the total is easy to find, and we can just use the total and subtract the one that is the complement, which is 1, and to get the 127 ways of at least one head. So that might be a little faster than to add up the 7 plus the 21 plus, okay, I didn't even finish counting the other one. That just takes way too long. But you can do it if you want. If you do it as the longer way, doing all the other 7 cases and add it up together, you will also get 127 ways. Okay, which way do you want to do, right? So if you have time, maybe you can add all 7 cases and see if what I say is true and challenge me. Okay, I would love that. Okay, so if you want to count at least one head, which we have 7 cases, and add it all up, then, see if it's the same way, same answer, 127. I would love to do it with you. Okay. All right. Okay, I'm going to do number 16 and maybe have you do the next few questions and then compare answer. Okay, so 16, we did one in 12.2 that's similar to this. If you are choosing 4 diamonds, you are not looking at all 52 cards. We are looking to choose from the diamond, how many diamonds are there, right? Remember there's 13 club, that's black, and 13 spade, that's also black, and 13 diamonds and 13 hearts, right? That makes up the 52 cards in the deck of cards. And so if you are choosing specifically diamond, you are not choosing from the 52, you are choosing from the 13 total diamond, you are choosing 4 out of that. Okay, so make sure if you are choosing the specific, you are not choosing from all 52, you are choosing only from the diamonds, and that will be the 715 ways. And why is a combination? Because every time we do deck of cards, the order in the deck of cards does not matter. It's considered the same hand when you switch the order. Okay, so the deck of cards is always combination. Okay, and make sure that you are not choosing from all 52 if you want specifically diamond. All right, so 17, we did enough of that. I hope that you can do it. So try to do 17, 18, and then we can compare 19 and 20. Will be a little hard, so we'll come back and show you how to do 19 and 20, but let's do 17 and 18 on your own and see if you can get comfortable with that. Okay? Okay, hopefully you have some answers to compare and not just here to copy. Okay, so number 17, hopefully that's pretty straightforward. It's a FCP, Fundamental Counting Principle, because it's 2 different sets, the skirt skirts and the blouses are two different sets, and so if it's two different sets, we cannot usually do the combination permutation or the distinguishable permutation. So it's 21 outfits. Hopefully you get that one right, and if you do, give yourself a pat on the back. Okay, number 18, same thing, because it's restaurant week, right? Restaurant week, we have the prefix and one main dish, one side dish, one dessert, and one beverage from each, right? And so make sure you know how to count the choices. So this is 4 different sets, and so we cannot use combination permutation or distinguishable permutation. This is fundamental counting principle, and make sure you know how to count. The choices are always separated by commas. So we have 3 main course because there's 2 commas, and there's 2 side dish because there's only 1 comma, and then 2 dessert, even though it looks really weird. Monkey feet for dessert doesn't sound appetizing at all. And then we have 4 beverages. And so altogether, when we multiply, we get 48 prefix meal choices. Okay, and so hoping that we agree on the answer, and there's no other way. Only fundamental counting principle works here because it's 4 different sets. Okay. So 19 and 21 is a bit hard, okay? So you have 31 flavors of ice cream, okay? So you have to first, when you go to the ice cream shop, you have to first choose cup or cone, so they know where to put your scoop of ice creams, right? So you have what? How many choices for the cup or cone, right? So cup or cone. And that is 2 choices. But after that, your 2 scoop of ice cream, whether you put, if you tell them that you want a peppermint and chocolate, the 2 scoops, which one they put on the top or on the bottom, I hope you won't yell at them, right? So it doesn't matter the orderings. So you would do order doesn't matter, 31, choose 2 scoops, okay? So so this is kind of like partial fundamental counting principle. You have to choose the cup first and then choose the 2 scoop of ice cream. So this is kind of not very intuitive, but that's the way we do it because the 2 scoop of ice cream actually order does not matter. Okay, so you can actually have combination of 2 methods. Okay, so similarly, number 20, we have to choose the ice cream flavor first before we can make a sundae, right? You put the topping on later. And so again, there are 3 scoops of ice cream for the sundae. Hopefully, which order you put the strawberry, vanilla, or chocolate, I hope the ordering does not play important role here. You don't get mad if they don't put it in specific order. And so again, that's combination. 22, choose 3 flavors. And then you wanted to, after choosing the flavor, you want to choose the topping. So you would times it by the toppings, right? So 5 toppings to choose from, and choose the 2 toppings. So which one they put on first, hopefully it doesn't matter to you, it will taste the same, right? So when you find out each combination, again, because they are different sets, you cannot make it into one combination. You have to treat it as 2 different combinations and then multiply them together, right? So the first combination, you have 1,540 choices, and then the second one, you have 10 choices, so you multiply them together, it will be 15,400 options for your sundaes at Dave's Ice Cream, okay? All right, so I'm not sure if you are comfortable now. We have what? 4 more questions, right? 4 more questions to call it a day. And you think we can maybe stop the video now and do this next 4 question and come back to compare answer? Okay, so again, I can't do all the work. I'm going to get so good at it. You have to do the work to improve, okay? Even when it's making a mistake, you still improve. Okay, so let's do that. Again, I hope that you have some writings on your paper to compare answer. And number 21, we have 6 girls and 7 boys at the party, so a total of 13 kids. And if the table can only sit 5 of them, right? Maybe the rest of them should stand. And so my first question will be, is there positioning at the table, right? So the first boy or girl that you call, would you tell them to, okay, sit on the far left or something like that? Is there positioning, right? If you have an instruction to tell them where to sit, then there's some type of positioning. So I'm assuming when you're telling them where to sit, the instruction itself is a positioning, right? And so when every time positioning, labeling, title is involved, we say it's permutation. And we have 13 people. We are choosing to sit 5 of them. Even though it's boy and girl, they are combining the choosing. They didn't say 3 of them had to be the girls or 2 of them had to be the boys, things like that. So we can see them as one set. So that's why it can be permutation, 13 permu 5, and that should be 154,440 ways. And I hope that I copied the numbers correctly from the calculator. You can double check for me. Okay, and number 22, some people do get confused. Do I have 3 tasks? Or do I have 9 tasks? Okay, so it's important to know which one is the task. And I don't know if everybody saw the lock, the tumblers, that if you have 3 tumbler means you have to get the numbers to match this line here in the lock, right? Usually it's like the bicycle lock or something, and you have 9 positions that you are rolling the tumblers, right? So you have to stop at the line here, and you have like 9 choices in each one. It doesn't have to be 0, 1, 2, 3. I'm just making that up. It could be A, B, C, D, E for all you want, right? But you have 9 choices for each one of them, right? And so you have to know how many tasks, right? So you are rolling a tumbler, that is 1 task, right? So you have each tumbler to roll them to match the horizontal bar here is a task. And so I could stop at any of the 9 positions. So each task 1 is the first tumbler, right? And the second task will be the second tumbler, right? And the third task will be the third tumbler, right? And each tumbler, I have 9 choices to stop at, so it will be 9 times 9 times 9. And again, you have to kind of think about how many action or how many tasks I'm doing, right? Sometimes people think it's 9 tasks, are you doing 9 things? Okay, so make sure is there 9 tasks that you have to do, or 3 tasks, right? When it's 3 tumblers, right? So my answer is 729 for the 3 tumbler 3 task. Okay, so that's some question you might have to ask yourself. Okay, and again, hopefully you got the same answer as me, and even if you make a mistake, it's a good mistake, at least now you know, and I will keep my mistake, and so when it comes to the time, I make sure I don't make the same mistake. We have the tendency of making the same mistake if we don't set reminders. Okay, if you are like me, I always make the same mistakes, even though it was a mistake, take me a couple times to learn it. So leave the mistakes sometimes, to know what is a mistake is also important. Okay, so for number 23, we have 4 red balls. I'm going to use R for the red ball and the 5 yellow balls. So Y for the yellow ball and B for the blue balls. And so 4 red ones, 5 yellow, and 7 blue balls. I think total that is what? Is that 16? Is that 16 balls altogether? okay? And 4 plus 5 plus 7. So because they are putting it in a row, so this, even though the balls are not letters, but you can see it as letters if you use R to represent the red balls and Y for the yellow balls. So it's the same as rearranging letters in a word, even though this is not really a word, but it's rearranging the letters. And remember which method we use when we are rearranging the letters in a row. That's the distinguishable permutation when we have repeat letters. So we treat them as 16 of them as all order matters. The 16 factorial is the same as 16 permute 16 again. And so the 3 R's order doesn't matter. We're going to take away, the 4 R's, not 3 R's. I make mistakes. Aren't you happy your teacher make mistake? Okay, 4 factorial for the 4 R's, and then 5 factorial for the 5 yellow ones. That order doesn't matter, and then 7 factorial for the 7 blue. That order doesn't matter. And so if you put them into the calculator by the permutation or by 16 factorial, take away the orderings, you will get 1,441,440 ways. And I hope I copied the number correctly from the calculator too. Okay, so if not, you should correct it. Okay, so again, this one is distinguishable permutation if you write them as letters to represent them. All right, and the last one, 24, is a challenge one when we have the word at least, right? At least one boy. So we might want to count the total, right? So to get the total, we use the FCP. So it's what? 4 children family, so 4 tasks, and each task we have what? In each birth, you can have boy or girl, right? Boy or girl, so you have 2 choice. So 2 for your first birth, 2 for your second birth, because you can repeat the same gender again, right? And then 2 for your third child, and then the 4th child, you have another 2 choices. So altogether, you have 16 possible choices, 2 to the 4th, right? And again, to break down the number of boys, we could have 0 boy or 1 boy or 2 boy or 3 boy or 4 boy, because I'm only having 4 children. The maximum boys I can go up to is 4, right? So for each specific, I use DP, right? The distinguishable permutation. If it's all 0 boy, sorry, I made the boo-boo again. 0 boy is not all boy, it's GG. Yes, your teacher made a mistake. GG is 0 boy, right? So 0 boy here is what? Again, if it's the same letter, you only have 1. So all boy, you also have 1, right? All boys, you also have 1. But when there's a mix of boy or girl, then you need to use the distinguishable permutation to help you. And so 1 boy, I would have 4 factorial counted as all order matters, and the 3 factorial is the 3 G's, that order doesn't matter. And so we'll have 4 of the 1 boy choices, 6 of the 2 boy choices, 4 of the 3 boy choices, and 1 of the 4 boy, right? So if you add 1 plus 4 plus 6 plus 4 plus 1, and it does give you the total of 16, right? So the fundamental counting principle does give us the total, but when it says at least one boy, which one is counted as at least one boy, right? 1 boy is at least 1 boy, 2 boy is at least 1 boy, 3 boy is at least 1 boy, 4 boy is at least 1 boy. So the at least 1 boy is what? 4 plus 6 plus 4 plus 1, so that's 15, right? Is that 15? Or you can use the total, subtract the complement. Which one is the complement, right? The one that's 0 boy is not at least 1. This is not at least. This is the case that's not at least 1 boy, right? So we can use the total to subtract the one that is not at least one boy, which is one choices. And so you will get 15 either way, okay? So which method do you like? I like this complement method. Okay, so if you like the other one that you can count the 1 boy, 2 boy, 3 boy, 4 boy, and then add them up, maybe it make you feel a little bit more comfortable. By all means, even if it takes longer, if it makes you feel a little bit more solid, by all means doing it the long way, if it help you understand a lot better. Okay, so again, the answer is 15 ways. We want to choose a way we can understand instead of always the shortest way. Okay, so whichever way that make you understand, by all means do that. Okay, and I hope this helps, and let me know if I make any boo-boo, or I did it right in front of you many times. So if I do not catch my own boo-boo, you can let me know and talk to me, email me, or let's Zoom. Okay, thank you, and I hope to hear from you very soon. Thank you for watching. Bye.